All right, so here's a problem. We want to compute the vertical, deflection, and rotation at point C. That's here on this free end. We'll probably just focus on the deflection today. It says include bending energy and axial force. I'm sorry about that. The printer kind of took off the bottom half of that. But I did want to point out there's some additional data given here. There's a value for G and a value for K. Those are both information. This is information you would need for including shear energy, and we're not going to worry about that. So the first thing we want to do is let's calculate the deflection at C. You might remember for virtual work, we need to first write moment equations for the frame. Those will be our real moments, or moments due to the real loads. And then we'll come back and we'll do our virtual system, which will be a unit load at C, and I'll assume it's down. And then we'll get those moments, we form the products and do the integration, and we should be done. So let's start first with the real moments. So let's just talk about this for a second. If I were to cut this section here, AB, and looking at the total system, would you want to look at the free body that's below the cut or the free body that's above the cut? And you can make that choice. I think what I would like to do today, if it's okay with you, is use the free body above the cut and also put my local coordinate system to start at B and go towards A. So it would be 0 at B and be maximum value of 20 at A. So it would actually be going down. Now you can do that. You can choose your coordinate system to start anywhere, any origin you like. But you have to keep that. Once you make that decision, it has to be the same in the real system and the virtual system. And then I think this one's a little easier for you to see because we've done some similar problems. If I cut somewhere between B and C, if I want to do the whole left side or the whole right side, I think you can see the right side is going to be easier. And I can also do my coordinate system to start at C and head towards B. So both of those would be pretty easy to do. So with that kind of as my background, let's go through the details. So I'll start up here, and this will be the moments due to the real loads. And we'll start with the first piece that I cut. So I was interested in just doing this upper piece. Okay, so let me redraw that. So there's the kind of upper L shape of the frame. Out here on the end was my 10 kip load. And then of course I have this distributed load that acts along the whole edge here. Bless you. It is that time of year. And then I went out this morning and my car was a new color. It was kind of lime colored. Have you noticed that? It's interesting, my cats like to sleep on my car, so I had these really interesting abstract drawings in the lime dust of kind of cat paw swishes and tails, and it was very, very interesting. My children are going to appreciate it because on Saturday they're washing cars all day long. It's good to have teenagers in the house that need money. All right, little sidebar there. So what I'm going to do now is I'm going to run my coordinate system down from the top, and I'll just call it Y. This little cantilever piece, we already know that distance, it's X. So internally, I'm now going to look for my real moment. I'm going to assume it behaves like this. So I just need to find that moment as a function of Y for all this stuff. Oh, I did leave off that the load was 0.5 kips per foot. So let's get the concentrated equivalent force for that. So like we've done before, we know that the concentrated equivalent force is just the same magnitude as the area under the curve. And the area under this part of the curve is the base, which is Y, and the height, which is 0.5. So this force is just going to be basically y over 2, right? 0.5 being 1/2. And from the cut, we know the distance to the centroid is what? It'll be the base divided by 2, which just happens to be y over 2. That's just pure coincidence. There's no kind of big pattern there. So now I can sum moments. I'll assume right-hand rule for my moments, and I'll sum moments about the cut. And let's see what we get. So looking here at this moment, with my right-hand rule, that's going to be a negative moment, the internal moment m. About the cut surface, the force y over 2 also creates negative moment. And the force is y over 2, and the distance is y over 2. And just so you don't forget that, remember that's force, and that's the distance. And then about the cut, I have this 10 kip force. It's creating negative moment. The force is 10 kips, and the distance is 10 feet. That's interesting. So I should be able to solve for the moment. When I solve for the moment, what do I get? Well, it looks like this is going to be y squared over 4. And this is going to be minus 100. And that moment should have the units of kips and feet. So there's my moment equation in section AB for the real loads. And I'll even put the moment there, AB. Okay. Is there some way we can check that? Make sure it looks decent? Well, the easiest one to check would be probably when y is 0. So when y is 0, that means we're at this point right here. So all of this is gone. And what's the internal moment there? Well, it would just be 100 times 10 or minus 100. So that seems to work. If I put in y equal 20, what am I going to get? I'm going to get the reaction moment. But I never solved for that. But it would give us that. So it looks like the equation is acceptable. Now the next one we have to do, and I will indicate that we went this way, is the free end, and we're going to go that way. So for this moment, I'll draw the free body for that. We're going to cut it here. We still have the moment, the force at the end, 10 kips. And now I'm going to run my distance this way. I'll call it x. And then what do we have internally? Well, we have the moment. And that'll be the moment in BC. I guess I should have labeled this one AB. Sorry, I kind of jammed these two together. They look like they're somehow connected, but they're not. So now I'll sum moments for that at this cut surface. Right-hand rule for sign convention, equilibrium equal to 0. And let's see what I've got. So I've got my internal moment, which on my sign convention is negative. And then I have about the cut surface, the moment caused by the 10 kip force, which also is negative. And its moment arm is x. So it looks like the moment in section BC is minus 10x. And again, that would have the units of kip feet. So there, I got my real moments. So the next thing we want to do is let's look at our virtual system. So in that case, we're going to have the same geometry that we had before. So I'll quickly sketch out something that kind of looks like our frame. And now, since I want the vertical displacement at C, I come to point C, and I apply my vertical unit load. And I'm assuming it's down, so I write it down. Now, just like I did for my real moments, I'm going to cut the system here. And since I went with the upper portion, I'm going to do that again. You have to match them. And then for BC, I'm going to do exactly the same thing. So my free body diagrams are going to look identical, except the loads will be different. So now these will be my moments, and I'll use the lowercase m, and this will be for my virtual load. So it's a little boring, but I'm just going to redraw this thing. So there's kind of my little free body diagram for this cut from B to C. Except the only load on the system now is my virtual load, and that's 10 feet. And I'm still calling this, just like I already previously defined, that'll be the distance y. And what am I looking for? Well, I assume the real moment in this direction, so I have to be consistent. This will be the virtual moment in AB. And now I use my equations of equilibrium to find this virtual moment. So again, I'm going to sum moments, use right-hand rule, and we're going to sum moments at the cut. Make sure it's in equilibrium. So what do we have here? A little less complicated than before for the real system. So again, my real moment is a negative moment, my virtual moment is a negative moment. And about this cut, the virtual force also creates negative moment, and a distance of 10. So it looks like my virtual moment in AB is equal to minus 10. So now I'm going to do section BC. I am going to cut that bit here and look at the right hand side. The only load on that is, again, my virtual load of 1, and just like here where I assume this direction for my moment in the real system, I assume the same direction for my virtual system. Got to be consistent. And then just find that moment. Oh, I left a piece of information off. I called this distance x. So again, we'll sum our moments at the cut. We're in equilibrium using right-hand rule. So what do I have? Well, internal, my moment is negative. The moment in BC. And then about this cut, I have the moment produced by the virtual load, which is also negative. Force is 1, distance is x. So my virtual moment in BC is equal to negative x. Now, from my perspective, you're pretty much done, because you have the moment expressions throughout the structure for the real load system as given, and then for the displacement, you applied the virtual load at the point where you want the displacement. You've assumed a direction, in this case down, and you've written moment expressions for those. You just need to combine them and integrate them. So I've kind of run out of space on this page, so I'm going to lift this up. And we're going to try to see if I can pull this off. Yeah, I got another sheet here on the side, and let's transfer those equations and see what we get. So now the displacement at C is going to be what? Well, we're going to take the energy in section AB. So that's going to be an integral over the length of the line, which is from 0 to 20, of what? The real moment in our system. Oh, I'm going to put the E and I over here, and then I'll divide by it later. So the real moment in the system is minus y squared over 4 minus 100. That's the real moment. And the virtual moment over the same piece is minus 10. And that will be integrated dy. And then the piece for the second section from B to C, the limits of that integral are 0 to 10. The real moment there is minus 10x, and the virtual moment is minus x, and you'll integrate that dx. I think we might be able to pull this off. These don't look too terribly challenging, so let's see what we can do. So multiply everything by 10. I'm just going to leave that fraction there, so I'm going to end up with the first integral is going to be y squared, or 10y squared over 4. So that's going to be 10y cubed over 12 plus 1,000, and then integrated in y will be 1,000 y. And we just have to evaluate that from 0 to 20. Did I do that right? Looks okay to me. The second integral is just, what is that? That's just 10x squared, right? You integrate that, you get 10x cubed over 3, and that just has to be evaluated from 0 to 10. So this is where you guys are going to have to help me. Somebody put 20 into that. Oh, by the way, you can see all these values are going to be positive. So I'm going to get a positive result, which means I did assume the right direction. The value of C will move down. Does that make sense? I think so. So somebody put 20 in there, and 20 in there, and tell me what the number is. And somebody else do this. Oh, that's easy. That's 10 cubed is 1,000. That's 10,000 over 3. That's 3,333.33. That one I can do. I can't do this one. I can see this part is 20,000, but I don't know what that is. What'd you get? 26,666. For this first term? Yeah. So 26,666, probably 0.7, right? And then the last one we got was, we think this is 10,000 divided by 3, so that's another 3,333.3. Oh, look at that. You add those together, and what do you get? 30,000? Exactly? Wow. That's very interesting. Oh, I left off the units, too. So this should be kip feet cubed. So now I need to divide by E and I, right? What's wrong, Mr. Bells? You're looking at it.
I did those.
Okay. So now the numerical value will be 30,000 kip feet cubed, and now we have to divide by E and I and do some unit conversion. So 29,000 is steel. So 29,000 kips per inch squared. The I value is 1,000 inches to the fourth. And then, of course, there's 1728 cubic inches in a cubic foot. So you can see my kips cancel, my cubic feet cancel. I've got inches to the fifth over inches to the fourth, which is inches. And what do we get? 1.7. I'm guessing. 1.8. I'm revising my guess.
1.787.
Oh, pretty close. 1.787, which would be 1.79. That's pretty good. So any questions about that? I think that's a very doable problem. Let me say that again. I think that's a very doable problem. Maybe doable in about 16 days. Is that a big enough nudge, nudge, hint, hint, wink, wink? Yes, Mrs. Bell.
At the beginning, the vertical beam, you cut it and you did the top, you did everything that was above it. Why didn't you do the bottom, and how did that?
I didn't want to do the bottom because I didn't want to have to find the reactions.
So
That's the only reason. And the other thing you can do is, once you make that decision to work the top, you can choose your coordinate system to make it pretty reasonable. Now, in previous times, I always say, oh, your coordinate starts here and goes there. So even when we did cantilevers, we always said x was from left to right. So when you're looking at this little bit, it would have been 10 minus x, and it gets a little messy. But in this scenario, you can do it any way you like. You can choose your coordinate system any way you like. But once you make these choices, say for the real moments, then those are fixed, and you have to use the same set here. Not only the coordinate systems, but also the direction of the moments. If not, your signs will get all messed up, and it won't work out. Okay. Oh, I should probably stop this now. Any other questions?
Can you scroll up to the first page?